A trucking dispatcher named Miguel Ortega kept a spreadsheet for 3 years that nobody at his company asked him to keep. Every time one of his 40 trucks called in with a flat, he logged the time, the location, and the cost, not just the tire, but the tow, the driver's lost hours, the missed delivery window, the angry phone call from the customer on the other end. By year 3, that spreadsheet had turned into something close to an obsession because the number at the bottom wasn't what he expected. Flats weren't a minor annoyance eating into his margins. They were one of the 3 biggest expenses in his entire operation, right up there with fuel and insurance. 40 trucks, and a design flaw dating back to the 1890s was quietly costing him more than most of his maintenance budget combined. That's the story that pulled me into this topic, because once you start looking at the actual numbers behind flat tires, you realize this isn't a minor inconvenience we've all just learned to live with. It's a genuinely enormous, mostly invisible tax on almost everything that moves on wheels. And there's a fix for it that already exists, that's already been tested at highway speeds, that's already rolling around on hundreds of thousands of vehicles in one country right now, just not yours. So today, I want to dig into why that is, because the answer isn't really about engineering, it's about factories, and it points toward a country most people don't expect. Let's start with just how big this problem actually is, because the scale surprised me, something close. 2 1 in 5 tires produced worldwide ends up thrown away before it's actually worn out. A chunk of those, scrapped from flats and blowouts outright, and another meaningful slice destroyed early from uneven, were caused by running at the wrong pressure, which is its own quiet consequence of the same basic design. That's not a rounding error. That's 1/5 of an entire global industry's output going into landfills or recycling centers early, purely because the thing holding your car up is a rubber bag full of compressed air, and compressed air has exactly one way to fail: leak out, a screw, a curb, a piece of road debris, and 30 seconds later, you're on the shoulder. Now, here's the part that made me stop and actually think about it differently. Every solution to that problem for over a century has worked around the air. The spare tire in your trunk, run flat sidewalls, roadside assistance apps, tire pressure sensors that just tell you the bad news is coming. Every single one of those is a patch on top of a fundamentally leaky design. Nobody removed the leak. They just built better ways to cope with it. So, what does a tire look like when you actually remove the leak? Picture slicing a tire in half so you can see straight through it. In a normal tire, that cross-section shows you an empty chamber, because compressed air is the thing actually carrying the weight of your car. The rubber around it is really just a container holding that air in place. It's a clever design from the 1890s, and it's barely changed since, because air is cheap, light, springy, and does a genuinely great job smoothing out rough pavement. Now slice open an airless tire, and there's no chamber at all. Instead, you see a web of flexible spokes running from the center hub out to an outer band, sometimes shaped like a honeycomb, sometimes like a series of curved arches molded out of engineered plastic or fiber-reinforced rubber. Those spokes are doing the exact job the air used to do. When the wheel rolls over the road, the spokes touching the ground flex and compress to absorb the impact, then spring back into shape as the wheel keeps turning. The weight of the vehicle rides on the structure itself, not on trapped gas. And because the support is built into the material instead of sealed inside an airtight chamber, there's nothing left that can leak. Drive a nail straight through the tread, and you've got a tire with a hole in it that performs exactly the same as it did the day before. This isn't one company's pet project either. Nearly every major tire manufacturer on the planet has been chasing a version of this idea. Some pair an aluminum wheel with fiber-reinforced rubber spokes and have already logged serious highway speed testing on passenger cars. Others build around a double-arch structure designed to spread heavy loads evenly. NASA even went further, developing versions for lunar and Mars rovers using a shape memory metal that springs back to form no matter how badly it gets deformed, because on Mars, there's no such thing as pulling over to call for a tow. One detail that stuck with me while researching this: on several designs, the outer tread is a separate, replaceable band. When the rubber wears down, you swap just that surface. Layer and keep the entire structural core underneath the same logic as resoling a good pair of boots instead of throwing away the whole shoe. Industry estimates suggest eliminating flats and pressure-related wear at scale could keep somewhere in the neighborhood of 200 million tires a year out of landfills, millions of tons of rubber and steel that simply never gets thrown away in the first place. So this isn't speculative science fiction. It's finished, tested engineering with a genuinely massive environmental and economic upside attached to it, which makes the obvious question land even harder. If it works this well, why isn't it sitting under your car right now? And here's the thing, the industry already tried to answer that question once, about 20 years ago, and the answer they got back from real drivers was brutal. You've probably heard of run-flat tires. If you drive a BMW or a Mercedes, there's a decent chance you're riding on a set right now without realizing it. The idea was straightforward. Reinforce the sidewalls heavily enough that the tire can still support the car for another 30 to 50 miles, even after it's completely lost pressure. Enough to get you off the highway and to a shop instead of stranded on the shoulder. Automakers loved the idea because it meant they could delete the spare tire, the jack and the wrench entirely, and reclaim that trunk space. Then actual drivers lived with them for a while, and the reaction was not kind. Those same thick, stiff sidewalls that hold a car up after a puncture are also thick. Stiff sidewalls every other day of the week, which means a noticeably harsher ride over normal potholes and rough pavement. They typically cost well more than standard tires, sometimes dramatically more. They tend to wear out sooner. And worst of all, most run flats can't be patched after a puncture at all, because driving on one even briefly while deflated damages the internal structure in ways that are hard to inspect from outside. So a nail that would have cost you a cheap plug on a normal tire now costs you an entire replacement tire. The market response was about as clear as market responses get when run flats were offered. As an optional upgrade, almost nobody chose them voluntarily. They only ever showed up in real numbers when a manufacturer installed them as standard equipment and gave buyers no choice in the matter. And even then, swapping them out for conventional tires became one of the first things a lot of owners did after buying the car. Fleet operators flagged that run flats could meaningfully increase total tire costs across a large fleet. Several manufacturers have quietly been backing away from them since that failure isn't a knock against airless tires. It's actually the most useful data point in this entire story, because it tells you exactly what the market will and won't accept. Drivers proved loudly that they want the flat tire problem solved, but they will not accept a harsher ride, a higher price, and a tire that can't be repaired as the cost of solving it. Run flats asked people to pay more and get less. An airless tire that hits the right price point does the opposite. Same ride quality, same or lower long-run cost, and a problem that simply stops existing, which is exactly why price is the entire ballgame here, and why the next part of this story takes us about 7,000 miles from Detroit, because the thing that actually kills promising technology almost never turns out to be the science. It's the price, and that's precisely the puzzle China has solved, again and again, for one industry after another over the last 2 decades. Start with where Chinese tire manufacturing actually sits today, because it's further along than most tea people outside the industry realize. Chinese tire brands have been climbing steadily into the global top tier, supplying factory-fitted tires directly to major American and European automakers, running production at a scale that touches every continent. Chinese-made tires now routinely sell for meaningfully less than European or American equivalents at comparable performance. And that gap stopped being a story about cheap knockoffs a long time ago. It became a story about an entire supply chain, from raw rubber to finished product. Sitting inside one country that can turn around a large order in a matter of weeks, now lay the airless tire on top of that manufacturing base, because the fit is almost uncanny. A conventional tire is a genuinely complicated assembly. Steel belts, multiple fabric layers, several different rubber compounds, all stacked and cured together in a process with dozens of steps where things can go wrong. Many airless designs, by contrast, are essentially molded. You inject an engineered plastic into a mold, and what comes out the other end is close to a finished product, molding things at enormous volume cheaply, while iterating the design fast whenever something needs fixing, is exactly what Chinese manufacturing has spent 3 decades becoming the best in the world at. If that pattern sounds familiar, it should. It's the same arc solar panels followed expensive and niche for decades until Chinese factories scaled production, and the price collapsed by an order of magnitude. It's the same arc that played out with electric vehicle batteries. Over and over, the breakthrough happens in a lab somewhere else. And the moment the thing actually becomes affordable for ordinary people tends to be the moment Chinese factories start building it at volume. And here's the part most coverage of this topic completely misses, because everyone's been watching to see which company puts an airless tire on a passenger car first. While China quietly skipped that race entirely and went somewhere else first, Chinese manufacturers are already producing airless tires by the enormous batch, not for cars, but for scooters, delivery carts, warehouse robots, forklifts, and the small autonomous delivery vehicles rolling around Chinese cities. If you've ever ridden one of the shared bikes parked outside a subway station in Beijing or Shanghai, there's a good chance you were riding on airless tires without ever noticing, because that entire industry switched over quietly years ago and simply stopped having flats. Factories advertise honeycomb designs made from recyclable material rated to resist sun and acid rain and hold up for years in rough conditions, and they'll sell them by the pallet. There's a reason those vehicles got the technology first, and it has nothing to do with engineering difficulty. Think about what a flat actually costs a company running a fleet of 100,000 rental bikes or a warehouse full of robots. Every vehicle sitting flat is earning nothing, while someone has to physically locate it and fix it. Multiply that across a large fleet and flats stop being an annoyance and become one of the biggest line items in the entire operation. Airless tires erase that cost category overnight, which is why the switch happened fast, at enormous scale, mostly without anyone outside China noticing it had even happened. Every one of those wheels is practice. Every production batch makes the mold a little sharper, the material a little cheaper, the process a little faster. And all of that hard-won manufacturing experience is aimed, whether deliberately or not, straight at the biggest prize in the entire industry: the 4 tires sitting under your car. So the technology works. The manufacturing muscle exists and is already running at scale. The demand is obvious to anyone who's ever paid for a tow. Which brings us to the honest part of this story, the actual reasons you can't buy these for your car yet, and the one problem almost nobody sees coming. The first real obstacle is heat. A normal tire gets some cooling from the air inside it and from airflow moving through the wheel well. An airless tire is a dense structure that flexes constantly as it rolls, and all that flexing generates heat with nowhere convenient to go. At scooter or forklift speeds, that's a non-issue, which is exactly why those vehicles switched over already. At highway speed, sustained for hours in summer heat, it becomes a genuine engineering problem. And heat buildup is one of the main reasons this technology has struggled to jump from slow vehicles to fast ones. The second obstacle is weight. Replacing air with physical structure means adding material, and airless tires tend to come out heavier than the tires they'd replace, which drags on fuel economy. On an electric vehicle where engineers fight over every pound to protect driving range, that's a real trade-off, not a footnote. The third obstacle is the one that catches people off guard: debris. All those open gaps between the spokes that make the flexing possible are also open gaps that pack solid with mud, snow, gravel, and road salt. A tire loaded unevenly with frozen slush becomes an unbalanced tire, which you feel as a shake in the steering wheel at highway speed. Engineers are working on covers and shaped inserts to manage it, but it's an awkward problem precisely because that openness is the entire point of the design. And underneath all 3 of those is the deeply unglamorous reality that a tire is a legally regulated safety component, which means any new design has to clear years of testing before it's allowed on public roads. No matter how promising the engineering looks on paper, manufacturers have publicly aimed for consumer passenger car availability multiple times over the past several years, and those timelines have consistently slipped, which tells you a lot about how hard that last stretch actually is. And to be fair to the engineers working on it, they're not being cautious for no reason. Your tires are the only thing connecting a 2-ton vehicle carrying your family to the actual road surface in freezing rain and desert heat after years of neglect. With a pothole waiting around any corner, getting genuinely confident in a new design under those conditions takes an enormous amount of testing, and nobody wants to be the company that got it wrong. But notice what's conspicuously absent from that list of remaining problems: Not one of them is a question of whether the idea actually works. Heat is a materials problem. Weight is a design problem. Debris is a shape problem. Every one of those is exactly the kind of thing that gets solved by manufacturing a few million units and observing what breaks under real-world conditions, which is precisely what Chinese factories are already doing every single day on scooters and delivery fleets, while the rest of the industry runs slower, more cautious trials. So no, you can't walk into a shop this weekend and buy a set of airless tires for your truck. Anyone promising that by next year is guessing. But what's actually true here is more interesting than the hype. The technology works, and it's already been proven at real highway speeds. The open questions left on the table are heat, weight, and price, not whether the whole concept holds together. And if the pattern that played out with solar panels and batteries holds here too, the road to your driveway almost certainly doesn't run through a flashy launch on a European luxury sedan. It runs through Chinese factories molding these things by the tens of millions for scooters and delivery fleets and warehouse robots until the process is fully dialed in and the cost has collapsed, and only then climbing upward into passenger cars. Here's the thing worth holding on to after all of this. The tire on your car right now is a design over 130 years old, and its greatest strength and its only real weakness happen to be the exact same thing. It's held up by air. Take the air out of the equation, and the flat tire stops existing as a concept altogether. That spare sitting in your trunk becomes as strange a relic as a hand crank bolted to the front of a car. The engineering to make that happen is essentially finished. What's left to solve is the price, and the price gets decided in factories, not laboratories. Let me know in the comments, would you actually put airless tires on your own car if they showed up tomorrow at the same price as regular ones? Or does 130 years of trusting compressed air make that a harder sell than it sounds? I go back and forth on it myself. If this was worth your time, stick around, because there's more like this coming.